agenda.
Yeah.
But thanks a lot for joining us.
Thank you guys so much for having me. So I'm Ethan. Basically ended up at a startup and doing kind of image generation stuff, and thought I'd talk a little bit about like what that experience was like, what AI is happening now, and like what the future kind of looks like. So, breaking into kind of just like what my story is, current generative models, and what the future of that looks like. So who am I? I am Ethan Smith, frequently Smitty, better known by some. And I was the co-founder and lead of research at Leonardo AI, later acquired by Canva, also still goes under that name. I've always lived in Florida and have done a degree and always had a fascination in psychology and cognition, considering myself a self-proclaimed junkie for novelty. I started a degree for pre-psychiatry, thinking I would do med school at Wake Forest. COVID hit, switched to FAU, ended up doing a psychology degree instead. Didn't end up being able to like get priority in classes, so ended up pretty much just repeating my high school psychology in college, which gave me the free time to do other stuff, like learn AI and stuff. I casually did a lot of art and some freelance graphic design, and then I had a brief fascination with like technical stock trading, which was like, okay, wow, I'm predicting things from data, and just found the fusion of both of these things in visual AI. So I used to do some stuff around like procedurally generated art. So like these are a bunch of like fractal things, some photography and like Photoshop.
Make all of those?
Yeah. Some album arts for some random people and stuff like that. And then VQGAN plus Clip happened, which was like the first text-to-image thing ever. It was really bad, as you can see. There was this whole era where everyone just went around sharing these collab notebooks, and you would pretty much just get home from work or whatever, spin up a Google Colab notebook, and they can get like 6 to 8 hours of the free P100 compute, and it would take 40 minutes per image to get that. So what is VQGAN?
Ethan, question. In that era, did you have a name you went by? Like, there were all these people that are their real names, but Rivers...
Oh, I was one of the few people who went by my real name.
Oh, okay.
Yeah. But Rivers Have Wings is, classic.
Yeah, that was a classic.
Yeah. VQGAN, what is this? It's pretty much just an autoencoder with a discrete latent space. Part of the paper also described that once you discretize the latent space, you can train a transformer on it to generate images in that latent space and decode. But we only really need the autoencoder part. So from there, what is CLIP? CLIP is basically an open vocabulary classifier. It was trained by, you encode a bunch of images, you encode a bunch of texts. You basically do like a correlation matrix between the embeddings of each, and you want to encourage that the correct pairs match and the negative pairs do not match. So, and the two of them together, you could basically initialize a random latent, decode it, evaluate it with CLIP, and basically compare its image text similarity. And from there, you could backpropagate that loss and just keep on updating that latent, decoding, update, and update, right? So until you get an image that kind of looks like what you asked for. It didn't optimize well. So you had to do all kinds of tricks, and that's what a lot of these collab notebooks were, like trying to just optimize it and stuff like that. I had a few of my own contributions. And you would do something like take all these cuts over the image and do all these augmentations, and that helped it do a little better. Then came disco diffusion, which was like, now we did the CLIP guidance, like evaluating an image with CLIP as it's generating, and keep on pretty much instilling that text guidance, but doing it with diffusion. And it also took about 40 minutes, but it was like really, really nice to watch. Like I said, it's like watching cookies bake in an oven. And the images were just like amazing. I think there's still nothing like out there that quite like this. Part of the trippiness about it was that CLIP would evaluate the image at like small crops, and that would kind of lead to this like recursive effect. It would like look right here and be like, oh, I don't see you asking, you asked for a cat, and I don't see a cat right here. So then it would almost like start generating like a mini image within your image. So all kinds of things like a oil painting of a Tesla coil, and I was just amazed by it for a very long time.
So many images so quickly.
Yeah, I'm just trying to speed through it, just there's a lot of slides. Afterwards, Stable Diffusion came out, and you could now generate an image in a second, and the images felt like very high fidelity, and I was like, okay, how do you still make this like artistic? So I don't know. I just got caught up in just all kinds of random experiments. Like this is just taking the Wish You Were Here album cover and running a bunch of like kind of image to images on it. And on the right side was just clustering features over the course of a generation. Some things of like what I call lobotomy art, which is like purposefully breaking the model weights and just injecting noise in spots like that. Some other things, like I was training a background removal model that failed, and it had a really interesting effect of removing backgrounds incorrectly sometimes. And yeah, just some other stuff around like object detection. So this was like the whole community, where it was like this underground community. You could barely even find it. Like if you Google this, it wouldn't come up at the time. You had to just like know a person who knew a person. And pretty much everyone in this community, we would just all share what we were making. And almost everyone, like a lot of people ended up working in Stability AI. A lot of other people ended up at different startups. Everyone ended up at a startup or did freelance work. We were very early, and we were like, okay, I guess this is actually monetarily interesting. I, at the time, did a very, very long blog to this, because people started to come. There was a huge like influx. It started off like a couple thousand people, so started to hit like 30,000 and so forth. And I was, for whatever reason, very motivated to just write an entire blog, kind of like just a parameter search on everything, like what happens when you tweak all these settings and stuff. Our main founder came across my blog post, reached out to me, and I almost didn't answer, as like he had a NFT profile picture at the time, and I was getting lots of people asking for like crypto collaborations, and I was like, nah. But his message seemed earnest, so we went through with it, and then ended up doing a startup. And huge shout out to this guy right here, who encouraged me to write that blog, encouraged me to write everything, encouraged me to have basically an online presence with all of this. And ultimately it was like pretty much the whole domino effect of ending up right here. Very spurred on by him. So the timeline is, I was first reached out to in July. We started building in October. Shortly after the site was launched, and kind of it's like very bare bones, all the founders met up in San Francisco, which was crazy, as my parents were like, oh my God, you're flying out to meet these people and living with them in an Airbnb, and you don't even know who they are. Later on October 23rd, we kind of officialized a research team, which I led. We began work on our foundational model. 6 months later, it took a very long time, as we did not have many resources, so had to basically have crazy gradient accumulation steps. Launched our model, and then bought out literally a month later. And I think probably in total we're like 130 people now. So this is our foundational model. It really went under the radar. I wish we reported this somewhere. On a lot of these different kind of evals, like Gen eval and image reward, and these are like human ones, beat a lot of the big names, or at least came close. Just capable of doing all kinds of really impressive images, especially a lot of things with text in them. So a big theme of this was just kind of learning as I go. At the moment I was like first contacted, I had never coded before. I did some MIT App Inventor / Scratch, which was like in high school, but I had never really coded. After kind of just getting into the art of it and being at the high level and just tinkering with the settings in the Colab notebooks, I was like, okay, this is not enough. I have to understand how this works. So I started off pretty much with like baby's first Python, baby's first stats, and then kind of worked my way up to like linear algebra and all that stuff. A lot of just trying to get hands-on relevant examples. People who have been making like blog posts and YouTube on this have pretty much saved me. I tried to jump into the deep end too, which I call like a little bit of a rabbit hole hell. Like I was like, okay, let's start with diffusion. Let's go through the mass, and then like I couldn't even get to figure out the notation. And then I just kept clicking through links that were like, these are the prerequisites, and these are the prerequisites to the prerequisites. They just kind of talk as if some things are just expected to be known, which is fair, but it was tough initially. I ended up kind of taking on the approach, once getting all the basics down, is that I wanted to basically have at least good intuitions around everywhere as possible, so that if I ever did need to go deeper, I at least knew how to ask the questions, and could dive deeper from there. I think that was really important, as having to start building these things, I could have the niches of knowledge, at least in like image generation and stuff like that. But yeah, knowing how to talk on these things pretty much. Another thing is, yeah, wanting to have just a bunch of different perspectives on a topic. Thankfully, like a lot of different people write blogs on it and on different topics, and they each provide their own perspective. And once you kind of marginalize that out, you get rid of all kind of the bias and you really get to the meat of the matter. And yeah, started off with it just like blogs, YouTube, people, just making things really easy, Coursera, and then finally kind of graduated my way to like archive papers and stuff like that. And yeah, something I've become very interested in, having like only found my kind of calling now, is how do you get people to find their calling kind of earlier and stuff. I know there's a lot of people who probably really enjoy learning and probably are in a similar spot to me, but just never figured that out until now.
We should talk about that.
Yeah, sure.
Yeah.
Yeah. No, I'm pretty psyched by it. So yeah, kind of just like, what is it like to be at a startup? I think it changed a lot of my intuitions on like what a startup is. For one thing, I learned timing is very huge. It's very possible to be too early or too late. I think there's people who try to monetize like Deep Dream and some of this like earlier like artistic AI, and it like never popped off. It's also possible to be late. I think it's pretty hard to get in the door now, but we were movers shortly after Midjourney. Like I said, this was before Stable Diffusion, all that stuff. We didn't really know we were going to build off of that. So I think when you consider things like luck and probability of like the things going right for you, being right timing and kind of playing the game right can at least maximize your probabilities, but maximizing your probabilities isn't a guarantee. It's just like things can go right. Like for instance, we had a very low user count, and what really spurred our growth was that influencers just started making videos about us, which made them popular, which made other influencers say, if I make videos about them, I will also be popular. So pretty much this organic growth that got us like 1.7 million really quickly. The importance of a moat. I think that was something I felt was really important early on, and pretty much every VC and funder you talk to is like, oh, what's your moat? What makes you different? And no one really had one. I mean, I think, but a lot of people still made it work, especially in like how do you build a team and get something like generative AI that's like next level compared to everyone else right away. So yeah, I guess the importance of a moat was not as much as I thought. Especially since things are going obsolete by the second. I think it's just your ability to adapt is so important. And then there's something I call the big model pissing contest, which is basically like so many startups and other things are just like, they want to train the biggest model with the most parameters and stuff like that. And it's a feat to behold, but it doesn't necessarily guarantee you that you're going to be successful. Yeah, model size is only a proxy for like what the user experience is. And I think there's kind of the argument that like, I think in the long run, these kind of big models will be able to tackle anything and ideally cater entirely to the user experience. But there's a space to play in of like building on top of models, kind of just building like very, very solution centric building rather than trying to have a big model that just happens to do everything, right? Another thing was that, yeah, even giants falter, is that I expected to pretty much just get steamrolled by Google by the second they woke up from their hibernation. It never happened, and you will find this to be the case. We can kind of avoid, we can kind of, as a startup, you can move very quickly and avoid that kind of bureaucratic friction that is unfortunately the reason that Google does not ship. And yeah, something else is, I think if you plan to stay around and grow, you eventually need to think on like big picture intelligence. I think everyone kind of has their flavor of AI that they're currently building on, but ultimately, I think that you have to imagine that people are going to start like putting all their assistants and AI directly onto your phone and iMessages and stuff like that, and it's like you need to start thinking on the kind of the big picture, I think. So what's now for us? We are attempting to build a world-class research lab in just a very wide array of applications, AI applications. So it's pretty much everything from very kind of foundational level research to like LMs to trying to like suss out like safety applications and things like that. And yeah, ultimately developing kind of intelligent systems that can operate an ecosystem of tools. I like to talk about it as language model as an operating system, trying to answer the question of like what is the intuitive optimal experience with AI? How do you as a creator collaborate with it, or kind of have it take the tedious bits, but still, enact your full kind of control. You don't really necessarily want to use like a text prompt slot machine necessarily. And language is kind of the cheap interface that we've used for a long time, and it works quite well. It's very easy to provide text, but it's a bottleneck. It's inherently ambiguous. Words mean different things to different people. It's hard to get very granular control with text. So what is a better interface? And of course, building kind of into more multimodal models that take in just kind of more data, I think it gives you a more complete representation of the world. And yeah, if this floats your boat, do reach out. So the state of current generative models, this is kind of like an evolution or family tree of like how we got to our current state of things. So the general principles of generative models is that we need to be able to sample from their learned distribution of pretty much the data set, and we need to also be able to evaluate the probability of a sample or a derivative or an approximation of it, some exceptions, but for the sake of being able to optimize. So we have kind of some model families, and I guess what I would call computational families. So we have things like GANs, autoregressive models, variation autoencoders, generative energy-based models, diffusion models, normalizing flow, and then you have kind of computational families that they can take on any of these model families. They're just a matter of like what kind of computation works nicely, how information passing goes, and stuff like that, and kind of determined by what the hardware lottery a little bit. So we have like state space models, convolutional models, which are kind of the same sometimes in a way, and transformers. You have things like RNNs and stuff like that. And what you'll really find is a lot of these models like are at least very adjacent to each other, or like you can almost say like, oh, one's a special case of the other. People say that very frequently. So like for instance, I say diffusion-like because now there's a lot of different things like flow matching, diffusion, and stuff like that. You can make the argument that's a special case of a hierarchical VAE, which I'll have a slide on later. It's also kind of just a denoising autocoder with multiple noise levels. You had things like normalizing flow and generative EVMs, or energy-based models, which both kind of funneled into diffusion. I think that diffusion ended up being kind of the practical implementation of a lot of different traits that we desired in other models. And things like GANs, you model P of X implicitly through the discriminator generator objective. And as we'll see later, yeah, autoregressive and diffusion models have even a lot of similarities for some domains if you swap the frequency and time domain. So yeah, where did diffusion come from? I think some of the closest relatives are normalizing flow, where you want to basically transform a simple sampleable distribution into a complex one. But you are limited in kind of the transformations you can do because you need it to be entirely invertible, and you need to be able to calculate the Jacobian efficiently. You are constantly like renormalizing it as you transform. So this probability distribution, as we map it to the other one, might grow in space or decrease in space, but we want to renormalize it so we can still basically say this sample here will have the same, the probability of this sample in this like simple Gaussian distribution. We'll map it to here, and it'll have the same probability, so we can still treat it as the same, entirely deterministic, up to basically just scaling factor. Energy-based models are super, super simple, but the big trait from them that's important to take away is that you begin from something like a Gaussian or another simple distribution, and then you calculate a direction you want to move to get to like higher probability. So these two themes, like mapping a distribution simple into a complex, and kind of getting the gradient of like where I can move to a higher probability. So diffusion models, this is kind of like a powder toy thing where you have like, I just basically like drew a bunch of gas particles in a stick figure, froze time, and then unfroze it. And you can see that it just disperses. It moves towards higher entropy and just like becomes almost like totally uniform, right? And it's like, well, what if we could model that process in reverse? So something just got destroyed by entropy pretty much, and we lost all of it. And it's like, what if we can go back? So that's kind of what's happening. We have this data set of points of like basically all the coordinates. This is our data set of a dinosaur, and just pretty much destroying it and reversing it over time. These are not mine actually, but someone did some really cool visualizations on GitHub. Yeah, transforms a simple distribution into a complex one per time step, unlike normalizing flow, which does it like per layer. And it's basically, yeah, kind of the continuous case, and each transform is effectively a Gaussian convolution. Here's our data distribution. Basically, like every point is like a Dirac delta, pretty much more or less, and then just slowly start convolving it with a Gaussian, pretty much adding noise and adding noise and adding noise. And by the end, you get to basically a pure Gaussian. And then it's like, all right, let's try to reverse that. Yeah, I like to think of noising as like convolving with a Gaussian in distribution space, whereas like blurring is convolving the an image in image space, kind of, somewhat loosely. Yeah. So with diffusion, we end up with this kind of continuous trajectory. And now that we have this trajectory between these two distributions, like the data distribution and this other one, we can end up on anywhere on this path and just solve for it. So that's what we do. We basically end up somewhere on this path. The model predicts the direction in the vector field, and we just solve for it pretty much. You use a solver over time to just integrate over it. And I also like to loosely talk about diffusion as gradient descent, just as like a common example. Like, it's not entirely the same, but I think it's a useful framework to kind of analogize it to. So, in gradient descent, you initialize weights from a known distribution. You'll compute the gradient and update, and then just repeat until convergence. For diffusion, we initialize our pixels from a known distribution, and you will compute the probability gradient, or the score. Like, instead of backpropping, your diffusion model will give you the gradient of where you can move to pretty much towards convergence, and you will just repeat that until a final diffusion step. And you usually have something like a noise schedule, which is the rate at which noise is removed, which you can kind of think of analogous as decreasing learning rate a little bit. There's also the perspective of them as basically being the modern Hopfield network. So they share some similarities in that, like Hopfield networks, they kind of learn these patterns, and they're pretty much these points of low energy, and yeah, you pretty much run a Hopfield network to follow the energy field to a minima. Similar deal with diffusion. You initialize, you find yourself in this space that is pretty much just high energy, and we just travel along our probability gradients pretty much. And I think kind of this aspect, yeah. So the idea of like Hopfield networks is you have like this kind of partial query or a perturbed query. So this is our learned pattern, for example. We noise it, or sometimes you'll like remove half of it, and as you run the model, you'll end up back at your pattern, or the most kind of like adjacent one typically. And you get to this idea of like denoising, self-healing, or a database with partial queries. They're all really kind of similar concepts, I think, here. There's something known as image to image, which is basically like, I will take an image, I will only partially noise it, basically kill off the high frequency details, and then start running the denoising process from there, and pretty much just like rewrite the high frequency details while maintaining the low ones. So you can see it's the same structure, but then we kind of become like something more photographic over here. And the idea is that we have our space of images, and we have our space of like drawn images. We noise it with kind of the forward diffusion process, like the noising process, and suddenly now we've convolved these distributions that are like very, very tight, and they have no connection with each other, and now they're overlapping. And from there, we can now sample in the other direction, and as we follow the probability gradient, we can end up in the other domain that we want to get to. So, just some other examples. And how do you get to P of X ultimately? So it's a Markov chain, like autoregressive formulation, pretty much. The whole deal is that this is our known distribution. We sample from a Gaussian, and then every consecutive step is moving from a noisy step to one less noisy step. So if we imagine we have 100% noise, and then we map to like 99% and 98% noise and stuff like that. And what's nice is everything is a Gaussian. We sample from a Gaussian, and then all of our transitions are modeled as Gaussians. And yeah, so basically you don't actually output the standard deviation in practice, but you can. But your model will basically predict the mean, pretty much, of the original denoised image. That's one way to do it. There's some nuance there. And yeah, this is the forward process, pretty much going from less noisy to noisy. So we have two directions we're moving in, and they're both modeled as Gaussians, these transition probabilities. Sorry. So the noise schedule is pretty much the amount of noise added per step, and we can talk about this in a cumulative sense. So we say if we add 0.01 standard deviation noise over and over and over again, you can get to the cumulative amount of noise from any point. And the sampling is very, very similar to, is very, very similar to the idea of like Langevin dynamics, where pretty much you're sampling from a distribution by like following the probability gradient and just repeatedly adding noise to where we are. But the amount of noise is decreasing over time based on that noise schedule. It's also called annealed Langevin dynamics sometimes. So this is kind of the analogy to variational autoencoders. So for a variational autoencoder, you'll have your observed variable, and you'll have an encoder that maps it into a latent variable. Alternatively, we have a less noisy state that gets mapped into a more noisy state. Or we can imagine this is the data mapping to like pure noise, but over many steps. On the other side, our decoder is the latent variable mapping to a data space. And for denoising, it's the opposite, going from noisy to less noisy. And yeah, for generation, typically for a VAE, you sample your latent variable, and sample your latent variable, then map back to data space. Same vibe, sample your latent variable, which is just a Gaussian, and it's over many, many diffusion steps. So hierarchical, as there's several stages pretty much. And yeah, they both follow this idea of maximizing elbow in their derivation process. And yeah, you kind of want the noising process to, you want your learned denoising process to kind of approximate the denoising, or noising process. Sorry, I have that backwards. And typically for a VAE, you try to learn your encoding process at the same time. That's how you're able to compute your posterior pretty much, or approximate it rather. But for diffusion, our encoding process, or noising process, is like, we don't need a model for that. We already have that. So that's why we don't really need the KL term to guide the encoding process. Like normally, for a VAE, you have to not only teach your encoder to encode something that is faithful so that it can be reconstructed, but also, it needs to match something like Gaussian. But since we have our encoding process is just our natural noising process, we don't need to do that. Yep.
It seems kind of nice that you don't have to learn the encoder, but also maybe there's a better encoder than noising, than adding Gaussian noise.
Yes.
What do you think? Do you think that we should bring back the idea of learning encoders?
Yes. There's actually a really interesting paper. I think it's on the other side, but basically there was a work that was doing, they still do a noising process, but they make the noising process learnable. So you'll use something like a normalizing flow to map your Gaussian into another space, so that gets learned as well. I think it is a little tricky. Like otherwise, you start to lose some of the properties if you want to learn the whole thing. But I think that's the best I've seen for a learnable forward process, pretty much. Neural flow, I think it's called. I can share the slides as well. I have everything in citations too. And yeah, just a quick thing on where did VAEs go? The classic VA formulation at a time was pretty much something that we thought was going to lead to very, very generative, strong generative models. I've seen, there's a lot of works on hierarchical VAEs and all these other different approaches. Unfortunately, they haven't been super performant. So that's why I say I think we kind of evolved into diffusion models from some of these nice traits that we can kind of extrapolate or evolve with. So I think, yeah, VAEs have kind of taken on other roles. For one, they're typically used for mapping data to a latent space, so we can work our generative models in a smaller, more efficient space. I say less V as they're closer to just plain autoencoders. And then I also say that we have some occasions where we see things that kind of look like variational autoencoders, although they aren't trained that way. Something like an image captioner really feels like one. If for example, everyone is now training these text-to-image models, which are kind of like decoders of text in a way, on synthetic captions. So you go ahead and you map an image into a very, very, very verbose caption. We'll say an image is 1,000 words pretty much. You can look at this readable text as almost like a latent space in itself. So we've now stochastically used an image captioner model to encode into our readable latent space, which follows the prior of natural language, and then decode pretty faithfully into something quite similar. So, yeah.
Is this a work or paper? Is this a real example?
Yeah. I found this basically real life image. I just used ChatGPT to caption it, and then I used our model I just fed that caption to our model.
That's really cool. So there's a project going on in the lab that's doing similar text.
Oh, really? Yeah. Yeah, there's some I've seen where there's some papers that like train an encoder of text, but they don't require the text to be readable. Like, so like basically everything gets like totally optimized out the wazoo. And in doing so, the text is much more compact, but it's totally illegible. And maybe there's like one or two words that like kind of seem like related to your image. So that's why I say like it's it's kind of like following the prior of natural language to some degree. Ultimately, the diffusion derivation is like very long, but pretty much at the end of the day, it's just your model predicts the noise that was added to the image, and it's just a mean squared error loss with it. That's it. The reason why we predict noise is because one, the MSE between two Gaussians is the cross entropy, so that's a nice property to have, and you can predict noise and then you can just subtract it. So there's some papers that will predict the velocity term. There's some papers that will predict basically the noise endpoint of the trajectory, and there's some that will predict the data endpoint of the trajectory. Though in general, you will almost always see people just predict the noise or velocity is actually pretty common too. Yeah. You have basically SDE and ODE samplers, or solvers, I guess. Basically, the way we compute an update step is, I mentioned that you can either predict the data point or you can predict the noise that was added to the image. But to get to the previous step, or the less noisy one, because that's ultimately what we want to do. We don't want to like jump to the very end point. We just want to take a small step. You will either predict this directly, or predict the noise to remove and end up with a prediction of the data endpoint, and then just take a small step, just an interpolation, pretty much. Just a graphic of that. This is basically our image over time as noise is slowly denoised from it. Predictions of noise over time, and then here's our predictions of the denoise sample. These are all just like linear transformations of each other, pretty much. Yeah. And you can see, it resolves shockingly quickly. Like even, right here, you still have a pretty good prediction of what it looks like, even though here it's totally uninterpretable. Just can remove the noise quite well. So we start here at something like very noisy. We make our prediction, which is right here, but then instead of just jumping to it, because this is not a very good prediction, we would like to refine it, iteratively refine it over time. We say, let's just take a small step, and then we'll rinse and repeat. And by doing this in kind of this stepwise manner, and especially in like adding noise to it in between steps as well, you can keep on refining your prediction instead of just trying to jump to the end. You really kind of have to do this. Like if you just try to predict the entirely denoised image from just a straight Gaussian, you just get a blob, which is not very helpful. So what kind of prediction can you do from just pure noise? Like we're ultimately trying to predict what the original image is, and the best you can predict when you have absolutely zero context is just the mean over your entire data set, pretty much, right? So there's also discrete diffusion, which sometimes goes by that name. If you've heard of like Muse or Maskit, among others, you have a discrete vocabulary of tokens. So you'll have pretty much a whole board of tokens, and those will be your image. They'll get encoded by something discrete like VQGAN, and those tokens will either get mutated or masked. Masked being kind of mutated, kind of looking like noising, and my dad, and masking being kind of like an absorbing state diffusion. I at least like it a little better than kind of the autoregressive formulation. I think the raster scan of image tokens feels really, really awkward. Like, why should the bottom right token of an image have the most context? So it would look something like this. It almost kind of feels like a game where like you have like a board of cards and you're playing like memory, and you flip over a card and stuff like that, and you slowly learn more about what's there. So you'll pretty much just run this, make a whole prediction. You'll have a distribution of possible image tokens. And initially there's going to be a lot of uncertainty, like almost uniform distribution, right? Like what can we really say that goes there? But we'll take a sample. We'll just like sample something, and we get a dog's mouth. Okay, cool. Let's run it again. And suddenly now these spots very adjacent have like a lot of context. Like obviously if there's a mouth there, then there's going to be an eye there. That's quite. So now like our distribution is much sharper. Here's maybe there's still some ambiguity. We don't know where the dog is. It could be outside. It could be behind a green screen or something like that. Yeah, and it's kind of like a wave function collapse for procedurally generated video games, pretty much. Where you might be generating the path of like a dungeon or something like that, and you're like, okay, well I just placed a tile here for a straight path, so I can't put a path that goes there, right? So as you pretty much just sample more tiles, you gain more certainty about what's there. And then, yeah, some experiments I was doing actually was kind of just showing that diffusion could be similar to spectral autoregression. So the same way people say multiplication in frequency space is convolution in like data space, kind of. Same vibes. Basically, you can decompose an image into its Fourier transform, get all its frequencies, and then just kind of like autoregressively go from low frequencies to high frequencies and just place them one by one. And here's some samples of I trained this model on a data set of flowers. So it does work, which is really cool. There's someone else who did a post on it that I was pretty inspired by. And basically, they made the case that images follow this kind of power law distribution of frequencies where our low frequencies are high amplitude and the high frequencies are low amplitude. Gaussian noise, white noise, is pretty much totally uniform. So as you add the two together, and you start increasing your noise level, they overwhelm the low amplitudes first. So naturally, noising kills off high frequencies while preserving low frequencies. And as you add more and more noise, it starts to kill off or overwhelm the lower frequencies. So yeah. Why have diffusion and autoregression claim the throne? Why did everything else die out along the way? I mean, a lot of them, to start with, GANs are very fragile. Normalizing flows weren't expressive. VAEs had things like posterior collapse, or they couldn't be expressive enough. There's all kinds of things right there. In particular, diffusion and autoregression, they use more computation. You can get a very long computational graph. Like you can do diffusion over 1,000 steps to generate an image. And it's like you decompose a problem into many subtasks rather than trying to do it all at once. But the nice thing is that it's entirely parallelizable during training. So you almost get the perks of like extending a problem with like an RNN, but you don't have like the pains of vanishing gradients and all that stuff. Yeah. So pretty much, yeah, like diffusion, for autoregressive models like language models, you'll simultaneously predict every next teacher forced token from the previous. And that almost becomes like a very, very large batch of examples simultaneously. And for us, for like diffusion, when you noise an image, you can just kind of just do the expectation over many different time steps. Diffusion also has the aspect of iterative refinement. To some degree, if you kind of make a mistake, we add some noise, you can keep on pretty much overwriting your past mistakes to some degree. And then just empirically very convenient, stable, it scales well, and probably just greater expressiveness. I also kind of have a perspective of liking to talk about like attention models and diffusion as like hypernetworks, which kind of gives them an extra dimension of adaptation. Like attention is something where we dynamically create like our weights on the fly for mixing, and diffusion is sort of like applying gradient descent, like a learnable gradient descent value.
Quick question.
Yep.
This is super analogous to like the AlphaZero works where they compare like training computation versus test time computation. I guess ChatGPT is now also like thinking about this, right? Have people done this for diffusion where I guess a VAE is kind of like a one-step encoder decoder, and the diffusion is like an n-step test time, more computation at test time. Have people done like compared like what's like the pre-training computation, what's like if you need this level of performance, you need this much pre-training computation or this much like test time computation? It
doesn't end up working the same. I guess like back in the day when like first diffusion like first came out and stuff like that. First people did like annealed Langevin sampling, which had like an outer loop and an inner loop of steps, right? That would take forever, as you would do something like 1,000 outer steps and like 5 inner steps or something like that. So it's like a crap ton of steps. Alternatively, the first diffusion models did kind of like 1,000 steps. Now we have samplers that can get it down to like 4 steps with like really good quality. And you can actually increase steps on some of these models, and like in rare cases it can actually not improve because of things like exposure bias. As you're seeing your own output, and I think in continuous spaces, I guess it's like more vulnerable. But yeah, I guess the overall trend is that it doesn't improve a ton, increasing your or like having more steps
a new link now.
Yes.
Oh,
So I guess some of the current trends of like what people are trying to do now in diffusion, everyone wants to make it faster. The holy grail is like, can we do it in one step, or does that inherently like break what makes it good? There's an interesting synergy with GANs. As you know, GANs, we are modeling the data in generative distribution, and we know they're vulnerable to all kinds of collapse. Like your discriminator can become too good, and it very, very easily separates your data in generative distribution. But in convolving them with Gaussians, or noising them, suddenly our distributions are harder to tell apart. So, you know, the noising aspect actually kind of regularizes the training of GANs, and GANs kind of help diffusion in other ways. Switching to flow matching, this is really funny, is that like pretty much a lot of people are now doing flow matching, which is actually really similar to diffusion. You just do a linear interpolation instead of kind of like this spherical interpolation thing we have. I keep on thinking, like, if someone came to me and was like, okay, make a model that, you know, does kind of generation by like kind of like this gradient descent, or like, you know, following the probability gradient. I feel like I almost could have come up with this with an infinite amount of time. I don't think I would have come up with this. So it's weird that the more performant one is easier, but yeah, learnable forward processes. So first, map Gaussian noise to another space with like normalizing flows, so we still have, you know, pretty much the tractability on it. And then something, very interesting that actually some work on at MIT is being done here is varying the noise level per the position of data. So I guess for like video models and stuff like that, or other things in kind of autoregressive formulations, instead of, you can sort of do like a sliding window of different noise levels for each position. And there's some other ones that are just saying like, okay, you know, we're diffusing an image. Why not just make every single pixel on its own noise level? You can cover more ground, they say, like basically cover that combinatorial space better. And yeah, there's some evidence that autoregressive formulations still win. They perform some better in some cases. They're also inherently more flop efficient at the expense of not being able to parallelize their generation. And yeah, I guess it's kind of coming to the perspective that maybe diffusion is better suited as a very, very powerful decoder that can, you know, still hallucinate all kinds of details, but you could basically do your autoregressive in this still like very deeper semantic space, because yeah, we can kind of phase our generation into many steps of like different hierarchies, which I'm very interested in. Actually, I talked about this in the next setting, so yeah. So what does the future generative models look like? There's some things I think that are like very adjacent, and I could say like this is definitely going to happen, and then some things that are much more speculative. So the near future seems to be like tokenize everything. Everyone wants to do kind of this chameleon implementation where it's like you tokenize images, music, actions, anything, and you kind of imagine this autoregressive transformer or language model as like a central operating system that can interface with your computer or other models or your phone or pretty much anything. And you know, you can, it's almost like, yeah, this idea of like coding in natural language and or like a command terminal in natural language. Yeah.
And for this, would you imagine having small models that one of them does the music tokens, one of them does the whatever tokens?
Exactly. Yeah. I think yeah. As you're generating it and you're generating your music tokens, you will ultimately feed those to a decoder, potentially like a diffusion encoder that's like, you know, pretty robust and just yeah. I think there's a lot of power too, and like I think a lot of people right now are using language models to write prompts and then feed those words into another text encoder. Just cut out the middleman, just feed the language model's features directly into these. Like, you know, they're much more rich. I think we will double down on kind of like connecting and reusing pre-trained models together to accelerate training. You know, we use pre-trained text encoders to benefit the training of like diffusion image generators and stuff like that. And the bigger you scale your language model, the you know, performance improves. You know, it trains well. And then yeah, solving video. I think right now, a lot of the video models kind of just produce animated stills. They're not very exciting, and they can, you know, often they can't even get physics right, despite being impressive in some ways. I think a lot of approaches literally just took the 2D image generation approach and said, let's just add another axis and just have temporal layers going along that axis. I think we need a fundamentally different approach. Pretty much applying RL and search to LLMs, so pretty much how much can we stack up on inference compute. There's people trying to get them to basically play games where we can like track the answer and like have a good reward signal. generate synthetic data that we evaluate and then train on that synthetic data, like filtering out the bad ones. I don't think this will FOOM, meaning like I don't think we'll get into that recursive self-improvement. There's issues of reward specification. Something I think about is the alpha geometry paper, which is like you could solve these very complex math problems, which is impressive. But for example, they show a human proof versus a AI proof, and this was done in just a few steps, and it relies on pretty much the student's just good insight, whereas the AI model pretty much just brute forced it over 110 steps that are almost uninterpretable to read. I think of this idea of scaling inference time compute as it reminds me of like the monkey typewriter theorem. Like, okay, if you give a million monkeys a typewriter and you give them a million years, some of them will eventually type the answer to your math theorem and somehow even prove it, right? So I imagine sort of like using an LLM is like that, but the better the LLM is in its base state, the smaller that space is, right? So if we imagine that a language model will get these things right 1 in 10,000 times, maybe the next one will get it right in 1 in 100 times. It's still almost this brute force aspect. And really what becomes interesting is the harder part is, we can keep on sampling these ideas or proposals, but how do we know when we've got it right in this like 1 in 100 times, right? So something has to check it, and that's where things honestly become interesting. There's this idea of simulating many agents and having kind of all these agents vote on an answer, which is kind of like wisdom of the crowd, where like, there's a jar of jelly beans or something like that, and everyone takes a guess at how many there are, and the average happens to be the correct answer of everyone's vote, or very close to it. And then training on things like mistake checking, reflection, chain of thought. What's interesting, so this is the ARC challenge, which is basically Francois Fleury's, Francois TensorFlow guy. The ARC challenge is basically, it's like this, supposed to be kind of this like general intelligence thing, and even the O1 preview, like the best model, the best AI, OpenAI model, is only getting 20% on it, which is very, very far from the expected 85%. So despite the fact that the new model is impressive, it does feel like there's a fundamentally missing piece here. I guess there was a note here on like maybe simplicity or shortness bias might help for something like this. I don't know if that's going to give it the ability to just apply this kind of like really, really good intuition. But you think about like, the Occam's razor being very useful, and like kind of the simplest solutions often are best, right?
Question.
Yep.
What do you think would happen if you took the output and asked the model to just reduce the size and keep on doing that, and then use that data to distill it down?
In this case specifically, I don't know entirely how it works, but it's sort of like the solver does the most of the legwork. This like the symbolic solver does a lot of it, and they like fine tune the model a bit to the task. I don't know if it would be able to like turn that into this, right? I don't think so. I mean, there might be some way of tuning that, but this approach, I don't think it fits. I think relying on kind of these large pre-trained models that we have is like, I like kind of thinking of these self-supervised models that are tasked with reconstruction as simulators. They are kind of just simulating possible trajectories and plausible realities from like partial context and just extending on it. And it's like, well, we can use these things as world models. Either we can backprop through them, or we can just use them for teaching an agent and stuff like that. And you can kind of think of it as the agent's brain as a simulator of the world, and which it simulates itself. And this is a recent paper on, they taught a diffusion model to play Doom pretty much, it doesn't play it. It renders Doom based on the conditions of like input keystrokes and stuff like that. And what's impressive is you can actually play this for like 2.5 minutes straight or something like that, and the map is preserved. If you turn around, you will be in like the correct space. Everything is like spatially preserved, so it has some possible world state there, but I have heard people sometimes like your bullets go up instead of down or something like that, so it's not entirely accurate. LLMs are still a great candidate for world modeling and stuff like that. I think they're just, we've just gotten a lot of information in them, and they seem to predict like accurate happenings of things pretty well. Continual learning, I think, is very important. People will do things like fine tune, and you'll maybe like KL with the base model to preserve prior knowledge. There's the idea of using LoRa's to learn less, but also forget less. You can retain your past data sets in the mix, merge back with your original model. I read a paper recently that was like saying that if you train on all these new different tasks, but you do things like shrink your weights and noise them and reinitialize some every so often, that actually helps preserve learning, which they kind of described as like de-sharpening / noising your energy landscape. I think looking to dreaming for inspiration is like really interesting. How are memories consolidated? And there's like two theories of people in AI who want to talk about like what is a dream, right? One person was basically saying that your dreams are basically augmented samples pretty much, and you are training on your augmented samples to enhance your generalization and stuff like that. And then Hinton basically said that dreams kind of provide like your negative samples, and you are actually trying to reduce your activations to pretty much your hallucinated samples, and during the day you're trying to raise your activation to real samples, which I think is loosely how is the inspiration for like the forward algorithm, but I'm not certain. So yeah, there's I guess like something else is how can we scale the capacity of our models without having like crazy number of parameters, and part of that I think is how can we increase parameters without increasing flops as much, and then how can we increase neurons without increasing parameters as much. So that's some things like you have this external KV cache, you can pick up like a database of different things. Retrieval augmented generation kind of like increases your capacity of the model by having things in context. Experts are a way to have like sparsity, like you can have a bunch of parameters storing kind of capacity or knowledge, and just only sparsely activate them pretty much as needed, right? I think I describe experts as kind of analogous to that external database. There's a paper that does 1 million experts, but they're only like one dimensional each. So like I'm like, that almost looks like an external KV cache pretty much. And experts are good. Like they scale the amount of neurons and kind of capacity you have without scaling flops or parameters as viciously as like scaling with would, for example. And a really interesting fact is that Llama 405B, I did on some like pretty much napkin math. It has about 23 million neurons. The brain has 100 billion. But Llama 405B has 18,000 synapses or connections, or rather that's a parameter per neuron. The brain only has 10K. So it's like if we want to rival our biological counterparts, at least if we want to just hit that number, right? Scaling with is just an n-squared approach. It's very tough. We're not going to hit that kind of many neurons that in that kind of way. And yeah, just a personal interest. I think about kind of the like icing model of the brain, and I was like, can we kind of get like this nested expert aspect where effects at a very small scale can propagate effects to a larger scale. So like almost like a very small expert can yield activity in a larger expert or something like that. Do you have a question?
Yeah, brain is only 10,000. Is it 10,000 connections per neuron in the brain?
On average. So how does the brain do it? Basically, the brain will have something like one neuron might have 100, like 1 million connections or something like that, and then another neuron might have like 3 or something like that. That is something that is really like. I'll get to the slide, but eventually I talk on that. Yeah.
Also, I just have another comment on the fact. I think it might be an intuition for us to create multi levels of emergence in our neural networks as well. So because if you only have one level, then it's pretty much densely connected.
Mm-hmm.
But if you imagine, let's say, a neural network as an agent or as a unit, as a neuron, and then build something upon it again, then it becomes much more sparse.
Yeah.
So maybe more like our brain.
No, 100%. I agree. The issue that ultimately is like, at least in my perception, is that GPUs aren't the most friendly to this. Like if you want to have 1 million connections per neuron, and maybe you want one neuron to have that, you have to have like a 1 million by 1 million matrix, right, or something like that. It's just you lose the parallelizability, and you kind of like preset the number of connection to have, and a lot can be zeroed, but like basically we symbolically set the connections to 0, but you have to have that like giant matrix for things to work. I'm going to basically be crapping on GPUs in a few slides. So yeah, another near future thing is kind of the idea of like cascaded or hierarchical inference. Basically, going from a text prompt to an image, we need to somehow produce all of these bits to get where we want to be, but we can do it in steps, and we can do it in different spaces that have nice, perhaps like inductive priors that make that space a good space to model in. For instance, there's kind of the unclipped model, which maps from text embedding to image embedding, and then image embedding to image space. Or you have something like Worston, which does pretty much like different latent spaces of different sizes. And ultimately, the big theme, I think the near future is just more around practical usage and efficiency than super intelligence. I'm not too convinced that we'll see super intelligence for a little while. Yeah. And then, yeah, something I'm also interested in is like kind of that hierarchical adaptation. I was saying how like diffusion and attention have these like extra axes of freedom, where you have the idea of like model design that is adapting over time. You know, over like 20, 30 years, we've been working on models. Your model then adapts over gradient descent. This might be like months, however long you train. You have in-context learning, which is kind of like our next best thing to model state, although we don't really have like a latent state that's being passed from time to time. So this is like many forwards. And then you have pretty much the dynamic weight creation. With it, you have dynamic properties happening within a single forward, which I like to call baby hypernetworks. And if we think about it in this perspective, like what can we do that's potentially more expressive than just creating a linear transformation with attention? And yeah, like I guess like, you know, could we create nonlinear MLPs on the fly, or like other kind of transformations or stuff like that? A project I recently did was LoRa Discovery, is what it was called, and it was basically just a suite of a bunch of different methods to create LoRa's on the fly. And the principle is that basically you see all these people kind of fine-tuning their models, and really in practice, you know, there's a small slice of like what you actually want. I could theoretically fine-tune my model on pictures of random noise. I could, you know, train them on just flat white squares. I don't really want to do that. So why don't we kind of, you know, put in a prior over our search space and use that to our advantage? So there's a couple different approaches I tried. One is learning the merge coefficients of LoRa's. So I basically tried like 100 different LoRa's and merged them, and then also tried diffusion. And this is me. I basically had 136 celebrity LoRa's, and then trained the merge coefficients of all them. So this is fascinating in the sense that this is basically my face represented only in 136 parameters, or double the 260 something bytes, right? It's faithful enough. I mean, it's not very flattering, but. And then here's some samples from the LoRa diffusion. You could generate just like pretty much new made-up celebrities. With 136 LoRa's for a dataset to train diffusion model, that's not very much. So the trick that I did to kind of expand the power of only 136 samples was, we know empirically that linear merges of LoRa's are still pretty much like valid LoRa's. So I created a bunch of merge samples on the fly and extended the data set that way. Another area of interest is I would be very curious if GANs make a comeback. It doesn't necessarily need to be specifically GAN, but I think the aspect of distinguishing real versus fake is a very, very powerful, nuanced kind of like signal. And also the idea of just like having a criterion that adapts continuously during the course of training. Like, you know, tasks can kind of become harder. It's almost like its own built-in curriculum learning kind of. And yeah, the premise is like, I guess increasing complexity of models might warrant increasingly complexity of losses. I keep on looking, again, at kind of like what's happening in these video models, and I don't know the work that people are doing in open source, in Sora and all that other stuff, but you still get a lot of inaccuracies on like what happens in a video. Like things are just not particularly realistic. The pixels are convincing, and I think, you know, we are taking an MSE loss over pixels, but I wonder if, yeah, plausible realities are almost like a different objective from pixel perfect realities pretty much. Yeah, I guess something I thought about when doing kind of the LoRa diffusion project was potentially there's some kind of way to combine GANs to kind of like get rid of their mode seeking behavior, in that they should both have a loss component that drives them towards the real manifold, like pretty much, you know, like the samples they could produce should feel real, but then also have a loss that is almost like inverse density. to basically seek out things that are rare or interesting. I wanted to see if there's a way to like automatically find new lures that were still somehow convincing. The hardware lottery. What stays? Like what can we know will be like around still? Pretty much everything we do is guided by like what works on a GPU, right? So everything needs to be kind of have this parallelizable formulation. You want it to be written as a matmul, and it needs to be fully differentiable. And that has led upon the transformer. The transformer is like, we found this in 2017, and things have like not changed much. It is kind of, it's just like, it has great flop utilization. Everything is just says use a transformer. But these are really big design constraints. It's very difficult to get statefulness. There's a lot of things I would love to do. Like having a neuron with a variable number of connections is very complicated. Exploiting sparsity is complicated. If you want to have like omnidirectional flow, like say maybe you want to have a model that routes to one layer and then this layer and then this layer, like everything is just feed forward. It's a very static amount of like flow. Things like adaptive compute. Maybe I think about like kind of the chain of thought that O1 uses happens pretty much in data space. Like it pretty much just writes its own like scratch pad and talks over it. But maybe we want to do something like as it's running through the model, it detects it's a hard problem, and maybe we want to loop through it some more. Differentiable signals. Statefulness is like everyone has tried to make the transformer stateful, but it doesn't really go well with kind of gradient descent and like parallelization, right? But it would be really really nice if like we fed our tokens all the way through our transformer. At the very, very end, we have now reached these like very, very nicely processed states that are, they contain a lot of information, right? But then we just toss those out and go to the next layer, right? You can't preserve what has been built up here and do this, pretty much. Yeah. And I guess, I am loosely preparing myself for there to be a dramatic shift in hardware, like how we treat things. Like, I don't know, maybe one day we will be solving problems with evolutionary algorithms if it makes sense. Who knows? What will stay is probably, the model family that's invariant to hardware. VAEs, diffusion, autoregressive have existed since the beginning of time, effectively. We just now built them into GPUs. And maybe we can think about like what are the properties of the things that work right now? Like what are the traits rather than like, matmuls and specific things to that. For transformers, for instance, people talk about like the ability of inductive heads and copying, global receptive fields, autoregressive formulations seem very strong and flexible. All kinds of future hardware, like there's people working on thermodynamic computing, which is supposed to be almost like quantum computing, but it works. That's how they've described it. Biological-based hardware. And I'm not a hardware person, but I am convinced by the case that you do expend quite a lot flipping bits, and maybe something like analog, even though you have like you're more susceptible to noise. It's okay because like everything we do is kind of probabilistic, and it's kind of we know that you can quantize a model into 4 bits. Approximations work, so we can spin this on its head and say maybe we can use this environmental noise to our advantage, pretty much. Yeah. And something. I guess this is one of those like plausible futures, but I don't know. I think about how we are connecting a lot of pre-trained models together, and it's very nice to just connect a big LLM to kind of like use its features for another model. What if we kind of invoke the best models we know, pretty much? I could imagine basically, people eventually doing things like using encoding of features from pretty much like a brain or something like that. And that's sort of this aspect of like cutting out the middleman. Like right now, we train on human writing, human images, human everything, and just map it back into a latent representation. But it's like, what if we can cut out the data space? And because we've just communicated this latent representation mapped to the data space and then back. So pretty much just latent to latent. And there's already some startups using biological minds or as computation engines. Like they're just masses of cells, pretty much. And I'm kind of under the belief that these things are just kind of universal computation engines. They've just adapted. The ones that we have just adapted to the special case of simulating the experience, pretty much. And I guess what's nice about that is there's a lot. There's still a lot of questions on the other things like thermodynamic and stuff like that. Like what kind of hardware works, what kind of network design works. We know that empirically these models work. We just, you would just have to figure out input or output. In the long run, there's probably something synthetic that much improves, but I could imagine in the, a somewhat relatively near future that people might look to things like this. And yeah, just conclusion, future is wildly uncertain, especially on longer horizons. It's nice that at least our very foundational concepts are here to stay. I'm very interested in kind of hierarchical stratification on pretty much every dimension. And yeah, it would be good to just consider what kind of happens outside of our design constraints. What do we think about outside of this kind of hardware lottery world? And you'll see that there's a lot of people who have written about all kinds of ideas. I imagine almost anything you can come up with right now has been talked about in the 60s or 70s or whatever. Schmidt-Hoover has invented everything, pretty much. And we're only just finding it 30 years later, right? And now suddenly it makes sense on some piece of hardware. So, yeah. Thank you for having me.